Video number 5 is going to be our last video of this short chapter, and we're going to talk about some special relationships between similar triangles. You can think of them as some shortcuts, and then there's one in particular at the end that's just kind of a special case that pops up involving similar triangles. So the first thing we're going to discuss is something we have done in the past, and just asking, are these triangles similar to each other, these overlapping ones? And what we want to look at here is maybe 4 shortcuts, because we don't have all the specific values here. We only know really one angle is congruent in both triangles, which is A, because it's a reflexive angle. But we don't really know if E and D, they are corresponding angles, but we don't know if they're congruent corresponding angles, because we weren't told if these two lines were parallel or not. So we can't just assume they're parallel to say that these two angles are congruent. Same thing for B and C here. They are corresponding angles, but again, we don't know if they're congruent corresponding angles. So angle's off the list, angle-angle similarity. We do have some side lengths here, and we don't know the lengths of these two bottom pieces, so that's going to rule out side, side, side. So what about side-angle side similarity? Whoop, too far, too far. No, that's not what I wanted to do. Not what I, no, no, no. Come on, crazy thing. I just wanted to go back to there. There we go. So side angle side similarity. We know the angles match because they were reflexive angles. We need to check the two ratios of sides. So let's say I just take the 4 here from the smaller triangle, and it's going to correspond to the 6 of the larger triangle. And is that proportional to the other smaller side of the small triangle to its corresponding side, the 3? So is 4/6 equal to 2/3? Yes, that is true. So these triangles are, in fact, similar by side angle side similarity. So since the triangles are similar, the ratio of the sides are proportional. So that's where we get our, really, I guess this is where I wanted to do my 4/6 and 2/3 and check that that is legitimate. Now, here's where a little shortcut is going to come into play. If we know this piece is 4 right here, and we know the whole thing is 6, well, how much is really left over for this little piece? Well, it would be 2, right? And if this piece is 2 and the whole thing's 3, well, that means BC, this little piece, is 1. Okay, big deal. So what? Here's where we can look at a little shortcut. Notice the ratio of this piece to this piece. Okay, AE to ED. Well, that would be a 4:2 ratio. And then look at AB to BC. These two little pieces that together make up the 3. It would be 2/1. And notice that those two ratios are the same. They're proportional. But 2/1 isn't the same as our 2/3 ratio, but it doesn't matter. This is showing us a special relationship here, which leads us to the triangle proportionality theorem. Are we going to prove this is true? No, don't worry about it. Okay, but it's basically saying that if you have overlapping triangles and you know that these two pieces that really don't overlap, right? Because really this side and this side overlap each other, and the right side of the small triangle and the right side of the big triangle, technically they're overlapping on top of each other. So if the non-overlapping pieces happen to be parallel, then what we can do is take this piece over this piece as one ratio and set it equal to this piece over this piece that got split up as a ratio. Okay? So again, this says RT, which is that little piece, over TQ, which is the leftover piece, is equal to RU, which is the right side of the small triangle, over the leftover of the bigger right side. Okay? We're allowed to do that. Can you still set this up like we normally would? Yeah. I mean, you can go RT over whatever RT plus TQ is and set it equal to RU over RU plus US. You can still do that. That's fine. But this is kind of going to be a shortcut for us. It's going to give us less work to really do. Now, I do want to point out why this works, okay? So, are you going to have to prove this? No. But I do want to show why this particular thing works. Now, the first thing I want to do is I'm going to do the reciprocal of both of these ratios. And if I do them together, if I flip the ratios at the same time, it's okay. It is mathematically valid that I may do this. And you might go, why do you want to take the reciprocal of that? Well, you'll see here shortly. Because I want to split up these fractions. Okay? RT is technically over both of these, so I can look at this as RT over RT and TQ over RT. Right? These have common denominators, so I can add the numerators together, and that's what I would end up with right here. I want to do the same thing on the other side. Okay, I'm splitting up that fraction to have the same denominators, and instead of adding the numerators together, I'm splitting them back apart. Now, do you notice the first fractions on each of those, on each side of that equation? I've got RT over RT, which means something over itself, something divided by itself. Well, that's always 1. And then I got TQ over RT, which I'm going to leave. And then RU over RU. Well, anything divided by itself again is 1. US over RU. And I've got 1 on both sides. So if I subtract 1 on both sides, it gets rid of that and leaves me with TQ over RT, which is, this, just the reciprocal version of it, it's the same thing, over US over RU, which again is the reciprocal version of that. So that's why this thing really works out. We really have a factor of 1 that we end up getting that cancels out on both sides. Long story short, that's why it works. So now applying this thing. I've got overlapping triangles. I know that I have parallel sides here, so I may use this. Now you might ask, well, what happens if those parallel lines aren't there anymore? Can I still do this problem and set it up as 30 over 20 equals 2x plus 10 over x? No, you may not. You may not. Unless you can figure out some other way that these two triangles are similar, you may not do that. So again, we can just take this piece over this piece, 30 over 12, set it equal to this piece over that piece, 2x plus 10 over x. Now we can cross multiply. 30x equals, we have to remember to distribute the 12 into the 2x and 10. So we get 24x plus 120. Subtract the 24x over, get 6x equals 120. And x equals 20. And we're done. Second example. Similar type of thing here. Now before we start setting up, remember I always said, hey, look for those parallel line symbols. They're not there. So can we do this problem? And some of you are going, yeah, we can't do it, we can't do it. But I have been given some extra information here. These angles are 90-degree angles. And if I think about these lines being extended out and this line being extended out, if you really think about it now, those are corresponding angles. And I've been told that they're both 90. So I have congruent corresponding angles, which means I am allowed to put parallel line markings on here. So we can use our shortcut formula because these triangles are similar to each other. So we can take this piece over this piece, x plus 1.5 over x, and we can set it equal to this piece over that piece, 5 over 2.5. Cross multiply and solve is one option. I'm going to back up just a hair. In the past, I've told you with this particular ratio, since it has nothing but numerical values in it, if you can simplify it, it might benefit you. And at first you might go, well, that's got a decimal in it. It does have a decimal, but can 5 over 2.5 simplify? And if you realize, yeah, that's really a 2 to 1, right? If I divide both of these numbers by 2.5, then that would end up being a 2 to 1 ratio. And now I don't have to multiply with as many decimals. So this is just one option. You can still do the 5 over 2.5 and you'll get the same answer in the end. So cross multiplying this way, well, I get x plus 1.5. Cross multiplying this way, I get 2x. Subtract the x over, and I get that x is 1.5. And I'm done. Now, there's another kind of problem that doesn't specifically involve triangles, but it's almost. Okay, and that's why we call this a corollary. It's similar to the triangle proportionality theorem. Okay, and it involves parallel lines still, but kind of like an incomplete overlapping triangle set. Okay, if you look at these two transversals, if I were to keep going with them and keep going with them, eventually it's making a triangle, right? And so then basically this picture looks a lot like that picture. but you really don't need this top little piece up here. You do need this little top piece because there's where we're getting our 4 numbers from. This is kind of saying if you were to, extend on and make more layers here that were parallel and parallel, you could take these 2 pieces with these 2 pieces, and it's the same thing as if you had taken these 2 pieces with those 2 pieces. So the same thing applies. Okay, you're still looking for parallel lines. You can take these 2 pieces that use the same transversal and set it equal to these 2 pieces as a ratio that use the same transversal. And we'll look at an example at the very end, but I figured these are so similar to the triangle proportionality theorem problems that I'm not really going to waste time and make this video any longer than it needs to be. Now the last thing we will talk about, I'm not going to show you why this works proof-wise, is because it's very in-depth and not really obvious why it works. So I'm just going to skip the proof part of this. But it's called the triangle angle bisector theorem. It says if a ray bisects an angle of a triangle, then it divides the opposite side into 2 segments that are proportional to the other 2 sides of the triangle. Holy crap, what on earth is that even saying? Am I talking English? Don't know. Let's translate what this is telling us mathematically with this picture here. Number 1, if a ray bisects an angle of a triangle, here is our ray AD, and notice it is bisecting angle A. Notice the 2 congruent segments there. So CAD is congruent to BAD. So here's our ray bisecting our whole angle. Okay, part 1 done. Now what? It divides the opposite side. Our opposite side would be this, would be CB. It's dividing it into 2 segments, okay, CD and DB, that are proportional to the other 2 sides of the triangle. The other 2 sides of the triangle are AC and AB. Now there's 1 of 2 ways we can set up our proportion, okay? I'm going to show you one way. Really the way they present it is the other way. Now, I don't call this a triangle angle bisector theorem because it's a mouthful. I call this the Heart Theorem. And you might ask, why on earth are you calling it the Heart Theorem? Because what I do is I start at the bisected angle. I start here and I wrap my way around going this way, and I wrap my way, I'll use a slightly different color here, wrap my way around going this way. And these 2 sides that I went through, AC and CD, I can set up as 1 ratio. And I can set it equal to the other 2 sides that I went through on this other side. Okay? So I can say that AC over CD, which again are these 2 pieces here, and I started from my bisected angle, so I hit AC first, CD second. So I wrote AC first, CD second. It's going to be proportional to, again, starting back at the bisected angle, going through AB over finishing it off with BD. And now I can cross multiply and solve, whatever values are in there. That's the way I look at this particular theorem. The way really it's saying is that these 2 pieces set up, CD over BD. Okay, so this represents the left segment, if you will. This represents the right segment, is proportional to the 2 sides of the triangle. Now here's the thing. CD, we said, was the left segment. And so since it's my numerator value, I technically need to use the left side that is adjacent to it. So this would be AC. BD was my right segment, so I need to match it up with the right side of the triangle, which is AB. Now, is this any different than what I just showed you earlier? Well, let me redo the Heart Theorem here. The Heart Theorem I said was AC over CD is equal to AB over BD. Okay, this was the Heart Theorem. Then this is technically what the triangle angle bisector theorem is setting you up to do. Are these 2 different things? No, they're really the same thing. And how do I know that? Look at what happens when you cross multiply both of these. The AC gets multiplied with the BD. Does that happen here? Yeah, the AC gets multiplied with the BD. It works out. CD here gets cross multiplied with AB. Same thing happens here, just in a different order. Okay, so you can set this up 1 of 2 ways. And the only way you can really screw it up is if you take, a left piece and try to match it up with a right piece. You can't do AC over DB is equal to AB over CD. You can't mix and match your two pieces here. The ray is really dividing the triangle and saying this stuff over here can match up with this stuff over here. That's the way I look at it. That's where I get the heart from. So starting at the bisected angle, wrap around this way, you get one ratio. Wrap around the other way, you get the other ratio. Set them equal, cross multiply, done. So here's one example, example 3. Here's my bisected angle. So you got to make sure this is happening, that there is an angle being bisected. I'm going to wrap around this way. So I'm hitting 16 and 6. So there's one ratio. And if I'm going to wrap around the other way, I'm going to go through the x and then the 7. Cross multiply. We're going to get 6x equals 112. Divide both sides by 6, and I get, let's see, 16 for x. And that's it. Now, keep in mind, this 16 and 6, I'm going to backtrack just a little bit here. The 16 and 6, I could have simplified that fraction before I cross-multiplied. I could have recognized that really, 2 can go into each of those numbers, and I could get 8 thirds. And then cross-multiplied with that, and I'd get 3x equals 56. And I get, let's see, 1, 2, no. What did I do? What did I do? What did I do? Apparently 112 divided by 6 wasn't. 112 divided by 6, yeah, it wasn't 16, my bad. This ends up being 18 and 2/3. So backtrack that. When I had the original 6x equals 112. 112 divided by 6 is 18 and 2/3. AKA it's 112 over 6, which if I divide both those numbers by 2, I would get, let's see, 112 divided by 2 is 56. 56 thirds is also the same thing as 18 and 2/3. So sorry for the mistake, my bad. Example 4. Same thing we're going to do here. I have a bisected angle from a ray here, so this is the Heart Theorem. I start here, I'm going to wrap around this way, start here, restart there, wrap around this way. Now, this one's a little bit different because the 10, notice, is all the way across, and I really need to know what these two little sub-pieces are. Well, I know one of them's x. Well, how big's the other side? Well, if the whole thing's x and this piece is x, or if the whole thing is 10, sorry, and this piece is x, this must be the leftover of the 10 from the x. So if I took the whole thing 10 and subtracted away this piece, this is 10 minus x. There's nothing I can really do with that. Notice the 10 minus x piece plus the x piece. Notice the x's cancel out because I got minus x plus x, and I'm left with 10, which is the whole stinking thing. So now I can set up here and say 6 over its little segment piece, which is 10 minus x, is equal to the other way around would be 8 over the x. Can I simplify anything before I solve? Not really. Cross multiply, just make sure you distribute with the 8. So I get 80 minus 8x equals 6x. Add the 8x over, and we're going to divide by 14. So let's see, I don't think this really comes out to be, again, a whole number. No, so we're going to simplify this. So what can go into 80 and 14? Well, we can always start with 2 since both numbers are even. And we get 40 over 7. Can anything go into 40 and 7 besides 1? No. There's x, 47ths. Now, it is also equal to 5 and 5/7, but how would I prefer you write your answer? Just leave it as 47ths. Don't give me the crazy decimal, because if you put this in your calculator and do 40 divided by 7, you're going to get 5.714285714, and there's really going to be no end to that decimal. Don't round it. Give me the exact answer. Give me the fraction, preferably the improper fraction. The last problem I want you to do, and I'm going to give you a little hint here, this problem is not the Heart Theorem, right? There is no bisected angle. This goes back to the corollary to the triangle proportionality theorem, okay? So you can set this thing up, solve it. There is another little trick to it, which I'm not going to spoil, but set this one up, solve it, and we will discuss it the next day in class. And that's all for video 5.